Alright, hello everyone. June the 16th. Alright, let's try this one today. Number of ways to reorder array to get same BST. Given an array nums that represent a permutation of integers from 1 to n, we're going to construct a binary search tree by inserting the elements of nums. Well, I need my pen. Gotcha. Pen and pen. Paper and pen. Alright, what do we have here? Okay, 1 to n, and we are going to construct a binary search tree by inserting the elements of nums in order into an initially empty binary search tree. Find a number of different ways to reorder nums so that the constructed BST is identical to the formed from the original array. For example, given nums is 2, 1, 3, we'll have 2 as root, 1 as left, and 3 as the right. The array 2, 3, 1 also yields the same binary search tree. 2, 3, 1 yields the same. Wait, why 2, 3, 1 yields the same binary search tree? Wait, what do you mean by the same binary search tree? Wait, hold on. What does this mean? How's 2, 3, 1 the same? For the number of ways to reorder such that BST form is identical to the original one. We can reorder nums to be 2, 3, 1, which will yield the same. How is 2, 3, 1 the same? What do you mean by the same? What the hell? Three, 4. By inserting the numbers of nums in order. What do you mean by in order into an empty binary search tree? Wait, hold on. What does it mean in order? I don't understand. Find the number of different. We're going to construct a binary search tree by inserting the elements of nums in order into an initially empty BST. Find the number of different ways to order nums so that the constructed BST is identical to that formed from the original. We have 2 as root, 1 as left, and 3 as right. So 2, 3, 1 is 2 as root, 3 as left, and 1 as right. I mean, if you say binary search tree can be changed, the left child can be bigger, then I guess that's right. Hold on, let's try different examples. So the original tree is 3. Wait, hold on. So 3, 4, 5, 1. I don't understand. What do you mean by they are the same? You say 2, 3, 1. 2, 1. What the hell? Or are you talking about in 3, 4? Okay, hold on. 3. If we go right tree first, 4, 5, 1, 2. Okay, and 3, 1. So 3, 1, 2, 4, 5. 3, 1, 4. What does it mean, man? 3, 1, 2, or 3, 1, 4, and 3, 4, 1, 2, 5. 3, 4, 1, 5, 2. I have no clue. What does this mean? What the hell? By inserting the elements of nums in order. I think this means to in order in terms of the nums into an empty. And I don't understand. I don't understand this at all. What the hell? How is this the same? How do you yield the same binary search tree? Has the hell? What's this? I don't understand the question. What does this mean? I don't even want to know the tutorial. I just want to know what the problem is. Hold on. Anybody explain what the problem is? Wait, what? What does it mean? I just want to understand the problem in the first place. All right, who can explain the problem to me? Okay, question explained. As they occur, okay. For a fixed sequence of insertion, the number of binary trees generated is exactly 1. Wait, how do you generate? Okay, can you just explain this? 4 comes 5, 1 comes 2. We can generate the same. Huh? Let's see the example. Okay, let's see the example. We first insert 3. Next we insert 4. Yes. Then we insert 1. It's on the left hand side. Oh, the insert, it's not to put in. You don't know the binary search tree at the beginning. Oh, that's what it means. I think now I understand. So you have 2, right? And you insert 1. You have to insert on the left hand side. Then you insert 3, okay? If you have 2, then you insert 3. It has to go on the right side. Then you insert 1. I was trying to see, you already know this tree and you're trying to put it in. I was like, it doesn't make any sense. All right, now it makes sense. So you have a 3, then you go 4. It has to go on the right side. Then you go 5, it has to go on the right side. Then you go 1, it's the left hand side. And then 2, yes. And you generate this, 3, 1, 2, 4, 5. Or 3, 1, 4, 5, 2. Or 3, 4, 1, 3, 4, 1, 2, 5, and 3, 4, 1, 5, 2. That's what it means. All right, I'm gonna read the question again. We're going to construct. Okay, that's the key word. You construct the binary tree from scratch, by inserting the elements in order. I was thinking you are filling in the numbers. Like, it doesn't make any sense. Okay, now you're constructing. Okay, so when you're constructing, that's actually a good question then. I mean, I already saw some hints, right? The hints is, you have the root. So the root has to be right, okay? So we got the root. Let's say we got 3. Then the next one has to be whatever the next 2 is, right? So it has to be 1, or it has to be 4 on the next level. Yeah, either 1 or 4. Yeah, okay. So we need to first know the binary search tree. Based on this, we can build it. So once we build it, we need to know what the second level is. And then, I mean, if you think about subtree, right? So we know we have 2 subtrees. So we have the subtree on the left hand side and we have the subtree on the right hand side. So if we want to know the total number of ways to build the binary tree rooted at 3, okay? Then we can say, if we know the total number of ways to build a binary tree rooted at 4, and the thing is, the binary tree that rooted at 4, whatever these elements, they are irrelevant compared to the ones on this side, because everybody here is bigger than this, which means if I insert things on this side and then insert this, it doesn't really matter. So whatever ways we have here is independent of the ways we have here, right? So if we have, let's say, 2 ways to do this, I can say I can do one way and then do something here, or I can do some other way and do something here. Are you saying that it can be a multiplication of the total ways? I mean, I'm saying we have to find the total ways of doing here, right? We have the total ways. Doesn't matter how many different ways to do it here. And I mean, it's 4 and 5, right? So if we just say 4 and 5, it's only one way, just 4 and 5, right? You have 4, and you have to put 4 first, and then you put 5. And on the left hand side, you have 1 and 2. So you have to put 1 first, then you put 2. But the relative order of these does not matter as long as 1 is in front of 2 and 4 is in front of 5. And that is fine. So how are we saying this? we have so basically we have 4 positions, right? And we are saying that we only care about the relative order, which is how the other trees, that's just how this tree is made, right? Hold on. Yeah, 4 is in front of 5, the 1 in front of 2. But that only works for this one, right? What if the tree is a little bit more complicated than this? Interesting. All right, the simplest case is, just by yourself, right? So just one way. And then if you have 2 values, right? If you have 2 values, the tree have 2 nodes. That's also one way. Okay? Now you have 3 values. So you have a root, okay? You have a root. And then if you have a one side, and then you say that's one way, and that's only one way, right? But then if you have 2 subtrees, and each subtree has one way, yeah, how do you handle this? How do you handle this one, right? Each subtree has one way, but they can shift their order. Because it doesn't matter which one goes first, right? So I can say this one goes first, or this one goes first. So same with here, right? I can say this one goes first, or this one goes first. And whenever this one goes first, then it's basically this and this, right? This subtree and this subtree. And again, this one can go first, or this one go first, right? So I can choose this one go first. Now there's only one subtree, so that's 1. Or I can choose this one go first. Then we have these 2 subtrees, and they can choose as well. So what I'm saying is, if we have a root, and then we have 2 subtrees and both have a root, and one of them can go first, so I can go this one, I can go one of them first, right? And then we do the other one. And then, that means we settle on one node. And then this one will have whatever subtree, and then all these can also choose which one to go first. And once that's done, the remaining can also decide which one to go first. So every single time, right? Every single time we are locking up on one of the tree node, on one of the subtree roots, and the remaining we just do choices, right? We just do choices. How do we code this up, right? So in this case, okay, we go back to this one. The root doesn't change, but here we'll have 1, 4, right? So we can say 1, 4, we can choose 1. Right? So we have 2 ways. And then when we do that, we remove 1. And on the left subtree we have 1. On the right subtree we have 2. Actually no, because we want to count the root. So on the right subtree we only have 1 root. So again, that's choose 1. Right? Okay. And then, well, it's not actually directly choose 1, because here it's different. If you choose on this side, if I choose 2, then it's only 1. And if you choose 4, then we have 2. No. No. Hold up. If we choose 1, right, then we have 2 and 4 when you choose 1. Then we can choose 2. Then it's just 4, 5. Or we can choose 4. Then it can be 2, 5 or 5, 2. Or we can choose 4. Yeah, that's because choose 4 is different. If we choose 4, then it's 1, 5. If we choose 1, that's 2, 5 or 5, 2. If we choose 5, then it becomes 1, 2. So therefore we have in total, oh, we have also a duplicate. Damn, man. No. 1, choose 1, 4. Well, choose 1. And we can choose 2. Wait, we don't have that. So 1, 2, 4, 5. Right? Or 1, 4. 2, 5. And 1, 4, 5, 2. Or 4, 1, 2, 5, 1. Or 4, 5, 1, 2. Hold on, how many do we have? Oh, one of them is the original. Oh, yeah, so it's 6 in total, right? It's 6 in total, but one of them is original, so okay. But that still doesn't resolve the problem. I mean, it's binary search tree, right? So every time you pick one, okay, what does the hint say? Divide and conquer. How many ways you can order x elements in x plus y positions? Don't understand what this means. I mean, we divide and conquer. I was trying divide and conquer, right? So we have the root, and consider the number smaller and the larger than the root. Okay, yeah, we have number smaller and number larger than the root. And then we want to merge the results. Basically mean like the total number of ways on the left and total number of ways on the right. We want to merge the result. How do we merge? And what are x and what are y? Yeah, I have a bunch of number that's smaller on one side and a bunch of number that's a bunch of numbers smaller on one side. And the binary search tree are already determined, right? Its shape is already determined. So the order you put it in, it will matter, right? So like in this case, you cannot put 5, but you have to put 4 first, because if you put 5, then you change the shape. Hold a second. So what are you saying? I mean, in this case, basically means we have 4 positions, right? We want to put 1, 2, 4, 5 in 4 positions. And there's a requirement on the order, and we have to do 1, 2, and we have to do 4, 5. It's just like on the left subtree, we have however many ways to arrange them. Okay, we already know. But the question is, how many ways we can put them into those 4 open spaces, right? We can arrange them into 4 open spaces. And once we have that, then the remaining is just to put the other value in, and we just multiply it by the other one, right? We just multiply by the other one. So it's going to be how many ways? So how many positions can we pick out of those 4? So that's 4 choose 2, right? In this case, 4 locations, 4 positions we can choose from. And we know we must put 1, 2 in it in that specific order. 1, 2, right? That's 1. So we need to find how many different combinations, or how many different ways we can choose from 4 empty spaces to place 1 and 2. And the answer is 4 choose 2, right? 4 choose 2, which is 6. So we have 6 different ways to put 1 and 2, right? And once we put 1 and 2, when that's done, we have 2 more spaces left, and that's to put the other, and that's just, so the answer, right, is 4 choose 2 times 1 times 1. Okay, and this one will be, we have 2 left, right? And then we'll have 2 choose 2 times 1, right? And that's 1, but we need to minus 1 again. And this is going to be, on this side we have 1, right? So it's 2 choose 1 times 1 times 1 minus 1, which equal to 1. Okay, I think we found it. So basically, it's a recursion problem. That is true. It's a recursion problem. And what we need to figure out, basically, is just what is the answer for each subtree. And we just need to merge it. I think actually I can solve this. Although it's still going to be no hint, but I can solve this. It's very straightforward once you understand what it's actually asking for, right? So we can say def dp, no, def divide and conquer, right? Divide and conquer, dc, dc, divide and conquer. So we're gonna have dear God, I have to build a tree first. Man, do I have to? If you don't build a tree first, how do you know? Holy crap. I do have to build a tree first. Huh. Like, if you don't build a tree, how do you know which ones belong to the subtree? You can see you have so many ways to build. All right, I think I need to build a tree. All right, I need to build a tree. I am not using, I just use node is gonna be a, dude, default dict? Holy crap. It's not even default dict. All right, no. Class node. Now it's per val. Okay, self.val equal to val. Self.left is none. Self.right is none. Yeah, I have to build the tree first. Okay, def build. Build. Really? Build? Yes, it's build. So we're gonna have the root and the value. Root can be node, and we're gonna have a value. We don't return anything. And then, what do we do? Nah, I think we can just I think we can just do this. Root equals node nums 0, right? And then we have at least one nums, right? Num 0. And then for any nums, node equals root. Can say while true. If node.val, right, is larger than n, while node, exactly, while node, right? No, while node. I need parent as well. Hold on. How do I build a binary search tree? So we have node, right? If it's larger, then we say we go to, if it's not none, if it's not, yeah, we can do that. We can do that. If node.val larger than n, node.val larger than n, actually we should say If n is smaller, this makes more sense to me. Then we go to the left subtree, right? And we say if node.left, node equals node.left, then we go back up, right? Else, then node.left equals to node n, and then we'll break. Else, if node.right, node equals node.right, else node.right equals node n, no break. Can we simplify this thing? Node.left equals this, and yeah, I mean, I don't remember how canonically it is done, but I guess it's fine. I mean, this I can use this to build. No hard feelings. This one is built. Okay. Now we're gonna let's call it solve. Okay, solve. I just need a root. Okay, I just need a root, and I'll return a value. I'm worried because I need to do combination. Oh, dude, I need to do combination. What's the? Oh man, we're gonna do. That's not true. It's 1000. We're gonna do. Wait, does math has Python math combination? I think it has. I think it must has. Math.com, it does. It does. Yes, and choose K. Yes, it does. It does. Okay, so we're gonna solve it, right? So we have this, and then we can check the left subtree. So we're gonna go left and right, and then we'll say if the left subtree has, we say if not node, if not root, we're gonna return what? Or return 1. I think it's return 1. Yeah, I'm gonna return 1. Otherwise, then we're just gonna say left ways and the right ways. But I also want to know the count. So I think we need to return 2 things, right? I need to return 2 things. I need to return the count as well. So we're gonna return the number of ways, and node counts. Okay, so 1 0, right? Otherwise we can say left count, left ways, and the left count equals solve root.left, and right ways and right count equals solve root.right. Okay, so once we solve both sides, then we can say what's the return value. Okay, and do we mod it? I think we can, right? It's just multiplication. We can mod it. Okay, we need a mod as well. Hold on. Mod equals to what's the mod? This is the mod. I'll do one without mod first. Okay, so it's gonna be the total, right? So left count plus right count. Math.com and choose, I'd say left count, right? So that's how many ways we can put the left in, and the left in we can have this many ways of combination, and then multiplied by right w. So that is the total number of ways. Okay, the total number of ways. So we're basically going to return this, and we're going to return solve root -1, whole thing mod. Okay, let's try. Okay, 2, 1, 3 is gonna be 1. This is going to be 5. And this is gonna be 0. But I suspect these might all pass, but I'm worried about more complicated cases. Number of ways. Note takes no argument. Jeez, man. Unpack. Oh gosh, should be 0. Oh, because I did not. I need to return count. So it'll be left count plus right count plus 1. Nope. This is not correct in the first one. That's fine. We can try to figure it out. I think we built a tree right. So maybe just on this. Let's see. Print root.val and left this, right this. Let's see. Oh my god, it's hard to see. So we're at 1, okay? Root.val. And then left. So I'm at 1, okay? Then left is 1, left count, right, and right. I think the left count, left ways and right ways is not right. But I need to multiply. Okay, so when we do combination, left count plus right count, that's 0. So this is going to be 1 times, that should be 1. That should be 1, right? So 3, so when I'm at 2, okay? I'm at 2. Hold a second. Why I have 2 times? That's interesting. Root.val is 2. Huh? Left ways is 1. Right way is 1. Left way is 1. It should be 1, 1, 1, 1. This RC should be 1. This RC should be 1. Why do I have a 2 here? That is very weird. What did we get wrong? Damn, I hope I didn't do this one wrong. Nah, this seems to be right. It's here. Something is not right. Because I got this 2 twice. I mean, how about we call it, I don't call it root. I don't know, maybe I just call it node to avoid any confusion. It's the same. Solve node left, right? So we solve node left. And the left comes in, which is a 1, right? And then we solve it basically empty. So we got 1, 0, 1, 0. And then we print 1. That's fine. And then with this one, we'll return 1 and 1. right? So I should have 1, 1, and then we do right, should have 1, 1, and then we print node, which shall be this with a 1. But I don't understand. Wait, what the hell is this? Hold a second. Let's just return -1. That's fine. I call solve node. No, not solve node. Solve root. Because root is equal to this, right? This is the root. Maybe I got wrong building the tree. Yes. Yes, I got wrong building the tree. Gotcha. Got a problem. There we go. I built it wrong. It should be, because I already did 0, so it should be from 1. Man, could do like a dummy value kind of thing. I don't know. You think this is enough? I mean, you can even try mod it here, right? We can try, you know, mod here. Mod. Not 100% sure, but I remember multiply should still do. Okay, so we can probably let's do some trial. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that shall be. Give it a shot. That's good. Let's try another one. Let's say 1, 10, 14, 12, 13. That shall do. Damn it. I missed 11. I can submit. Got this one. Wow. I'm very surprised. I mean, the difficult part is to understand the problem, but once I understood it, I mean, does the hint help? Yes, it does. I think it points to the right direction. I mean, this one, right, point in the right direction. This I don't really understand initially, but I was on the right track. Right, the most difficult part is to understand the problem. Once that is done, the divide and conquer hint was helpful, but the most important insight, right? Important insight is that the left subtree can be considered independently from the right subtree because everything on the left is smaller than everything on the right. Thus, the problem is converted to given n empty spaces to given n empty spaces, and then we have k values to insert first, right? And these k values have certain number of ways to arrange themselves. Then we insert the remaining m minus k values, which also have their certain number of ways of arrangement. Now the ways to insert the first k values is n choose k multiplied by the number of ways to arrange those k values, right? And then we multiply on top of that the number of ways to arrange the remaining n minus k values to reach the total number of ways to construct, right, both subtrees. We call it O n log n, right? Yeah, O n log n times, we can say O n, right? O n log n times the combination cost. Okay, I'm interested in whether there's a way to not build a tree first. You don't have to build a tree. This is true. You just DFS num directly. Okay. Left nodes. Ah, God. That is true. Holy moly, this is great. Oh yeah, it simplifies so many things. OM squared. I'm completely wrong. Oh, it's a Pascal triangle. This is not right. I thought it just... Yeah, this is actually not right. I mean, for me, I took ON. Now, this is ON. No, it's ON log n to build the tree, right? And after that, we do this. It's actually log n. Yeah, so it's us actually log n afterwards times combination. But here it's more complicated because we have this happening every single time. But I don't like it. I do not like it. I like my way, but the gist is the same, right? You use combination. Good. It's pretty good. I count this as a hint. All right. So yeah, that's it. That's all I want to do today. All right. I will end it right here and see you guys tomorrow. Adios.